here's a good example. A machine experiences a sequence or a series of shocks. Okay, each shock damages the machine with probability 5%. So not all the shocks are totally detrimental. Okay, some of them the machine weathers just fine, but then some of them actually inflict damage, and 5% of those are the bad shocks, independently of everything. The machine finally totally breaks down upon receiving the 6th damaging shock. Okay, so it may withstand 100 shocks, but it's going to finally just break down upon receiving the 6th bad or 6th damaging shock. So, what's the chance that the machine survives more than 10 shocks? Well, there's several ways to tackle this problem. Here's one way. First of all, I'm going to say, let's let t denote the time at which the machine breaks down. Okay, and we want to know the probability that t is greater than 10. That's the chance that the machine survives more than 10 shocks. Now, I'm going to use the rule for complements here because, if I'm going to try to solve this directly, I could use axiom 3 and have an infinite sum from 11 up to infinity, okay? But maybe instead, I'll just use the rule for complements and note that that's the same as 1 minus the probability that t is less than or equal to 10. All right. Now, so this is 1 minus, let's see, what's the probability? Actually, t can't possibly be less than 6, right? T has to be at least 6. So, isn't this probability is by axiom 2? By axiom 2. Should be just the probability that t equals k. 6 up to 10. Okay. 1 minus, I'm just going to repeat all this stuff. Now, what is that probability? What's the chance that t equals k exactly? T is a negative binomial random variable with parameters r equals 6. Right, and p equals, I guess, 5%. Okay, so I'm just going to replace this with, let's see, we'll have k minus 1, and what is r in this case? It's 6, I guess, and then 5% raised to the 6th times 1 minus 5% raised to the k minus 6. And you can put this in your calculator. Yes, this will take some doing. You have to, put a 6 in there and multiply this out, and then put a 7 in there and multiply out, and all that stuff. Be sure to subtract from 1, and I think you get 0.9999972 or thereabout. Okay. So now, what is the expected number of shocks that the machine can withstand? Before breaking. What is the expected number of shocks that the machine can withstand before breaking? Before breaking. Okay. Note that we're not actually asking for the expected time until the machine breaks. We want to know how many shocks can this thing withstand and sort of still be functioning and be on its last leg, so to speak. Okay, I think that's what it means. So, what we really want here is the expected value of t minus 1, I think. Okay. Well, so then that's the expected value of t minus the expected value of 1, which is the expected value of t minus 1, right? Now, remember t is a negative binomial, right? So we know the mean for this guy. It's r over p. R in this case is 6. P is 5%. At minus 1, it comes out to be 119. Finally, what's the variance regarding the time until the 6th shock? Or rather, what's the variance until the time of the 6th damaging shock? It's easy, right? You just plug into that formula. It's going to be r times 1 minus p all over p squared. And I think that comes out to be 2280. Okay?